result of compression here is result of tension. This is a tension failure in concrete. That's all it is. Tension failure here or here. And the loads cannot be, the tension failure cannot be overpowered by the longitudinal post-tension cables. If it could have been, this would have never deflected. Yes, we do have these guys up here doing something, and that's just because, Denny told them to. And that's what I'm sticking to, because he's the engineer, and nobody would have gone up that bridge and did anything without Denny Pate's approval. But now it appears that this money, the lobbying money, and look at the fucking smoke and mirrors in this article. You just wrapped it up in one little statement and said number 11, and then call it a day. Let me scroll up to the top. Blah, 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 blah. Smoking crap. And you go up to the top. Come on. Sorry about that, guys. Well, I gotta refresh the page so you can hear the, hear it. Okay, we'll let the 14-second duck commercial go by. The Florida International University bridge collapse outside Miami, killing 6 people, appears to have had a key flaw in its plans. This thing is everything, no key flaw. The whole damn thing. Here we go.
Looking over the
everything.
drawings and just doing a simple static analysis, stress analysis. The stresses.
Great, it's got a delay in it. Guys. Sorry about that. I forgot about the delay. We'll let this play. And David Beck. So we scroll down the bottom. Let me guys get you David Beck. David Beck, a New Hampshire-based structural engineer and construction manager with more than 40 years of national and international experience. He has blah, 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 offshore oil platforms, including bridge power plants, la, 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 la. I think we need an expert on post-tensioning, and your source data is shit. Let's go on. So it started as an idea for footbridge to get college students safely over this trail. But fueled by millions of dollars in available federal stimulus grants, what's this crap about? It's a Tiger Grant. Call it a fucking Tiger Grant. So, what's going on here? This is FIU trying to go around this soft stepping bullshit. I mean, not FIU. This is Miami Herald taking a turn on us. Well, he always took a turn as far as I'm concerned. It's a Tiger Grant. But fueled by millions of dollars in available federal stimulus grants. Okay, so now the Tiger Grant's not even in this topic. Florida National University doomed pedestrian bridge morphed into something far more ambitious. A gleaming testament to Florida FIU's lofty institutional aspirations and the linchpin in a grand plan to create a true college town in the neighboring working class suburb of Sweetwater. Okay. Well, now it's a working class suburb, right? Let me see what comments you guys got for me. All right, let me read the comments. Tim, yeah, I think that's you, right. You guys can see my mouse, so you see I'm reading where I'm reading. Airplane wind. I call it an umbrella for wind reasons. Yeah, right there. Well, sorry, Tim, you just beat me to my own statement. And I addressed that too, Scott. Yeah, they dead loads based on whatever your forces are the hurricane winds now. Supposedly they did wind tunnel testing. Hey, PE. Screen text is fuzzy. Let me see if I can tap it and get the focus in. Thanks, PE. I'm working on that now. Oops. Oh, okay. Oh, one more time. Here we go. Thanks, P. Good call. I think you see it now. Yeah. This is a small 50-meter press right. Regardless of the simplicity of the computers used, the lead engineer is responsible. Thank you, Doss. Yeah, Raven. That's your position, Raven. That's right. Yeah, cracks represent movement, right? One way or another, unless they're shrinkage cracks, when they're first developing. And then later on, you can get other cracks from other reasons. But during this stage of the game, shrinkage cracks are the only ones I'm turning a blind eye to. But that's indicating that you didn't do your concrete properly either. So shrinkage cracks indicates bad craftsmanship, bad craftsmanship because you should account it for everything: the drying, the wind, everything. At the bottom they put. What? What? Hey Scott, you serious? You see what Scott says? He says we are not responsible for any. At the bottom they put, we're not responsible for any calculations of measurements. Scott, they don't say that. Come on, man. You pull on my leg. Here we go. All right, let me get back to now this, and let me see if you guys got the screen on it. Let me do a split screen. There we go. That works for me. Crack drive sidewalk isn't worse than this is a cosmetic difficult. What crack are you talking about? Crack is representing movement. Cracking a sidewalk's not a problem if you got, if you again, I agree with them all. Tim, a crack in a driveway or sidewalk isn't worrisome. Yeah, that's true. It's kind of annoying unless you got water under there, or they didn't compact the earth. All right, so let me see if you guys can read that. Yeah, you can read it. I hope to the left. Yeah, I'm going to work on the left now. All right, but fueled by million, right? At FIU's ambitions grew, blah blah blah. The unconventional placement of diagonal supports in an uneven zigzag pattern along the bridge produced a complex structural web with a glaring weakness. Glaring weakness at a key connection point. At a key connection point. All right, so they're now saying this is Miami Herald. Remember, this would all be propaganda and everything else now at this point, because they're now making it propaganda from. Let me make this clear what I'm saying here. This is propaganda from the Miami Herald, because already 3-4 paragraphs into it, they're saying a that means singular, a key connection point. They're not saying anything else. It's making it clear now, their position. Apparently overlooked by designers at Fig Bridge Group. Overlooked is implying that, that's just stupid. And now you're also giving them overlooked, like it's a mistake, like no big deal, it's overlooked. Say 3 independent structural engineers, so we got the 3, who reviewed nearly 2,000 pages of calculations for the bridge so they had over 2,000 pages of calculations for the bridge at the Miami Herald's request. What? 2,000 pages of calculations? How the hell did you get 2,000 pages of calculations for that bridge? 2,000 pages? Maybe you did one calculation per page. And somehow you made up 2,000. I hear you, Scott. All right, scrolling down, next one. The weakness was likely a key factor in its fate. The weakness was likely a key factor in its fatal March 15 collapse. The independent engineers told the Herald. The weakness. Wait a minute, we got one thing now. It's the weakness. What the hell? The engineers believe Fig, significantly misjudged what would happen when a large amount of structural stress was placed on a structural stress was placed on a single diagonal strut. So you see now that Miami Herald is clearly pointing out the one, number 11. That's where the position is now with them. And that's it. So they hired echo chamber, all right? So they hired an echo chamber. A concrete brace that helps support the bridge. That's kind of evident, right? At the north end of the 174-foot span. That resulted in unnourished, I love this word unnourished, I read that a couple times. An unnourished strut. Sorry. An anchor that could not adequately bear the weight of the bridge. Okay, so we're going with that. So his evaluation says it couldn't bear the weight. So that means it's under compression. Okay, so it couldn't bear the weight of the bridge, and there's substantially forces placed on them when the span was lifted into place. Now you're saying it couldn't take the weight of the bridge when it was lifted into place. Wait a minute, make up your mind now. Over two supporting piers, the outside experts said. That joint is precisely where the bridge appears to have failed. So now they're saying it's a joint. So now we're no longer at the node, we're at a joint, and they're all joints, right? But we're referring to it as a joint at this point. And where some cracks began to appear. Even before the bridge was installed, over the 8-lane, okay, even before the bridge. We know, PE, I got this for you. Hello, everyone. Hello, Danielle. Danielle, somebody asked me to do this video when they sent me the link to that Miami Herald article, and they asked me to do a commentary, so here I'm doing it. So that's where we are. And I wasn't going to do it. I was kind of okay, and then I read so much of that article, I got triggered. My little amygdala got fired up. I got triggered with contrary statements they were making. So let's go ahead and give you an idea of this guy here. This is the post-tension rod. And I've already shown how this goes through once before. How it rips through the bottom of 11. But anybody new might want to see it. Basically, it's on the pedestal. These two have to stay here in motion. We have it rotating. So 10 doesn't fail at all until it hits the ground. Forces are still in the air. This does not till it hits the ground. 10 stays intact. So all our action is going down at the bottom here. But when we separate from this compresses down like really bad in the video. This guy crunches down like that. That's where you're getting all this damage, I believe, at that point, ripping through, tearing up, and sharing its concrete away from each other. I showed you how concrete can pull away so easily from rebar. Once it clears, this takes a bump down. This probably bumps there at that point. Hits the Jersey barrier here. As it starts ripping down, this starts ripping through there. This this takes all this in compression, starts failing, pulling the node down to the top of the deck. As it's doing so, this is still attached. It's still hinging at that point, because if it wasn't, it would be off in the air, right? It wouldn't be ripping through this. So give me that. So, but it has to stay here too. So we're there. Oops. Let me pull a screen out for you guys. Okay. We get the bump there because we have a little bit of bump in the. Ooh, yeah. We get the bump there on the side of the pier, if you guys can find that in the NTSB images. We get the ripping out of the bottom of 11. We get this coming down. This starts compressing, breaking 10 down to nothing onto the deck below. The node stays intact pretty much. Hits there, jacks up a little bit there. But it does take a shift and a bump back and forth. I think it winds up with something like that on top of the Jersey barrier. This is the scale, so whatever I do to one, it's going to react to the rest of the scale model. And again, I cannot make 10 fail in compression. I mean, 11. I can't make 11 do anything on its own. So they're all implying 11 is magically overloaded. And what's overloaded? So what happens when you overload a member? It buckles. Well, for it to buckle, it's also going to have to give some material. Number 10 is a known. It did not, this looks so much perfect until it hits the ground. As you can look at the video over and over again. Which means all the failures back here. You've got, yes, you have loads coming down 11. But we also have evidence that there is no shearing going on like that because of these guys having the pipes, the PVC pipes. And if you look up PVC pipe and shearing at 3-inch, 4-inch, and 5-inch pipes, if you can try to calculate which one's inside there, maybe it's 3-inch pipe, you'll see that the shearing is, you're going to do it about 700 psi. You're going to start shearing that pipe. So there's no forces practically at all it takes to shear it. And yet we have PVC pipe standing up above the deck. So if this is under so much load, what do you do? Hit that PVC pipe and go, oh my gosh, I'm just going to disintegrate now. I'm just going to just start crushing up because that pipe is just badass. That's how ridiculous that statement of shearing goes with me. And, but if you make this guy fail and this guy fail together, we need them to fail together because you can't have them failing individually because they go down together, as we look at the video over and over again. If they could fail separate, use compression, you're going to have to do 8,500 psi. Tension, you're only going to come down slightly. Now they have longitudinal post-tension cables in here. If they were near the top or even near the middle, that doesn't have as much power as being near the bottom of this because this is where the tension forces are interpreted. Let's say they were like right about there. Well, then you could probably figure out if you were going to do calculations on what the post-tensioning does. You'd probably only count like right about there as the thickness of your whole entire concrete. You wouldn't really give too much to the rest because it's not helping you. It's in a net neutral position at that point. Going back to the article and looking at your comments in a second. That's shadow of the charger. Let me see if I can lower it down for you guys on the phone because it's going to tap out. Oh, not even charging. Hold on. Make sure it's charging because I had a weak battery to begin with. And 57%. We got enough to rock it. All right. Scott Butler, laugh out loud. The reason this bridge failed is origami. Concrete bridge is heavier than a paper bridge. Darn it. I didn't think about that. So back to the article. Cousin It's here. Hey, Cousin It. Let me see what you got for me. Cousin It. Okay, back to the article. So the joint is precisely where the bridge appeared to have failed. So the Miami Herald is now making a precise statement now. I mean, they're not even leaving it open for data now. They're saying, so I'm saying again that Miami Herald now is, I don't know, it's very, very shady here. Is this part of the lobbying going on? That's what somebody wrote me. I'm just sharing that information. You guys know what I mean. So anyway, that joint is precisely where the bridge appeared to have failed. Why do we need to show that? What's going on with that? Strengthen the deck. Yes, PE. Well, they did it, the slenderness factor. It's just terrible in this thing. But it's concrete still. You still got all these forces. Ultimately, it's just craftsmanship. MCM built this thing. FIU showed that they had problem after problem with their placement of with following the plans. Just at the first glance, bottom deck falls north of 10. The rest follow. They followed Scott. Yeah, Eric. I think they had to go together, but ultimately, we can't have our cake and eat. It's just weird. I said it in a previous video just a previous live chat we did, that I would love to see one fail before the other. I can't do it, and ideally that you'd want to see these fail together to show that it's, oh, I'm pointing at the darn, so ideally these would work, this truss system works together. So with that said, it worked together, I've got to, they work together, that this fell because it couldn't take the load. Most of the load's down this far end, this section down. This is the one I find very interesting with the four with the four, the highest compressive loads on it all. The post-tensioning, which creates compression in this member. That it has 4 post-tension bars of like 389 kips. It's higher than all of them by 109, 100 and some change. And it's got 4 of them in it. None of the other ones have it on it. So that's why I think we don't see this coming apart, for one. But at one point, I think you create an imbalance in here, and more than likely, I suggest that it drove the force down 10 and not so much down 11. And so from there, if they're down here, if this whole system's working, and this is overriding this node, if you will, by having more forces in this crazy plate. Let's pretend like this plate is actually something you can create different forces on. And you can literally, because you created 4 here and only 2 in this direction, and then you detensioned it. At that point, you just got 4 on here. At one point, we know they detensioned it, right? So now we just got a load of 4 times 389 kips on this guy. So they're counting on that the loads will go down here, and why this? Because it's going to have let's just say that they have 4 on there because they decided that this bridge has got so much forces it wants to pull apart. It wants to pull apart at number 10. And I say that's evident by them putting 4 post-tension bars in it and putting it at 389 kips each for each bar. So clearly, there are some awesome forces that are being created right here. If that's the case, then that means the forces are down here too, right? I mean, logically, you guys can say I'm missing something. I'll be glad to talk about it because I'm talking live here. If that's the case, if the forces are so great there, that puts a hell of a force from here to here in tension, right? So this is supposed to be in tension, theoretically, tension. But it's still a load. It's still a load. So, and did it resolve? Did it start, even though it's in tension, are the forces resolving themselves right there? And then we get this opening. We get a tension break. Of course, they're together. And it's history then. Those cables, these longitudinal post-tension cables, can't resist the forces of this thing bowing down. And let's go back to the article, and I'll look at your comments. I'm tightening the focus up before I look at the article. Okay, here we go. So question, the original endpoint before they lengthened the bridge. Oh, I don't know. I don't think it really matters, cousin. It does matter. 10, I think 10 had, I did look at that. 10 had, what do you have there? Oh, I got cookies problem, Danielle. You got some cookies, you better give them to me. I'm not sharing those. I don't drink coffee. So you guys can have the coffee. I'm hoarding the cookies. Okay, as a consequence of the apparent design error, so now we're talking about it as a design error. The diagonal support, singular, at the span's north end was so overloaded that additional stresses put in it by construction crews tightening internal support rods on March 15th likely caused it to separate from the walkway deck. What the, you guys, I'm going to curse again. What the fuck is that? You just told me that your clothes, I'm stressed out. As a consequence of the apparent, you told me right here, if you read this, and these are the engineers saying this, it says, the diagonal support at the span's north end was so overloaded, so it's overloaded, it's under compression, right? It's overloaded, that additional stresses put on it by construction crews tightening internal support rods, they only tightened 1 as far as we know, they were working on number 2, on March 15th likely caused it to separate from the walkway deck. So the rod, how can it separate from the walkway deck if you have a rod through it? And it's under compression, it's pinned. It's pinned right here. It can't go anywhere. You're closing it. It's already this one's already tightened up, A or B, or I call it number 3. It's already compressed. It's the top half. They're working on the bottom with that section at that time. And they said the compression, reading out loud for you guys, let me look at it. cause it to set from the walkway deck. That additional tightening internal support rods on March 15th likely caused it to separate from the walkway. So when I'm doing this, when I'm actually pulling this together, I'm actually causing it to separate. Ridiculous. Just ridiculous. You're creating extra forces in there, but the forces are here, pinned here and pinned at the top. They create a compression here. You can have the failure in this plate crushing up inside here if this was not full of concrete. You can also have the node having pockets of lacking concrete, if you will, that could also compress down. It's compressing. It's not pushing. It's not pushing. This, if you remove this altogether, right? Then all the loads would be here on the as it comes down. You know, it's going to be like that. You're going to have some friction, if you will. It's going to stop it from moving over because it's under load also, so it's not going to want to move. There you go. Now you're sliding. I was trying to get the slide. Good. So you'd have some shearing in here at that point through here. This is in the way. But we can't get this to move. Let's just, theoretically, if we do that, we have to get it to move. But we've got indications showing it didn't move that way because of the pipes, the PVC pipes. So there's my trigger. Let's see if I can stop the cursing for you guys, but it felt good to curse a couple of times about this article. Okay, moving on. Consequences of the parent design, right? Right. The instantly sending the entire 950-ton span crashing to the roadway and a chain reaction of structural failure, the engineer said. Well, the accident killed one construction worker and 5 people sitting in cars at a stoplight below. Sitting in cars. Wow. See the comments. Third place, the article's point for failure. But isn't that the third place, the article points? Well, they said a point, single place. I don't know. You can point it out to me, cousin it. Well, Danielle, I don't count you. You got a mind like a man, so sorry. You gotta go along. I don't count you, Danielle. If you're watching this stuff, you got one of those man minds, one of those man brains, and a woman brain, which is a rarity. Because you like flowers. Don't think I didn't forget that. Cousin it might be a lady too. Darn it. Got me, cousin it. Are you a lady too, cousin it? You have to fill my date up. Are you a lady also? Oh. Oh, you got to press show. What a tits, Danielle. I don't know. Vertical. I'm reading over here right now. Just where my mouse is so you guys know where I'm thinking, where I'm reading. Well, we got concrete, Raven. And so, Raven, it's going to overload it. Remember, if we got concrete, we don't have steel anymore, man. We don't have, Raven. So, I'm saying man, all right. So, Raven, bird. So, we don't have steel. We got concrete. So, I don't know what this thickness of concrete can take before it finally fails. It'd been awesome if they did test each section and know what it took to fail each one under load at a joint. So you'd have this one and this one and then see what it would take to make this fail. That would have been an awesome test. And then you have an idea. And I guess you would use this, talking out loud with you guys, where you calculate the most forces on this design typical. And then you would say, okay, well, that means the most forces on this would be here and here. Let's take a section that's 10 feet wide, and let's go ahead and load that thing up and see what we need to resist. And then let's add a factor of, 4 on top of that. And let's do it with post-tensioning cables. But we have so many dynamics, as I said in the beginning of the video. This is not grouted down here yet. It doesn't appear to be grouted. So all the loads are now coming onto just the shim. So you've got 950 tons going on top of the shims. All of the forces on just on this little point load. You know, that's resisting going back up. What does that do? What does that do to this? That's just a hell of a joint at that point. You know, that's one hell of a joint. You just can't, hell, I don't care who says it. You can't make this move without, it just can't move theoretically without these two moving first. Canopy and the lower, this lower. You can make this buckle though, for sure you can make it buckle. There's no buckling. And possibly, as I said in one video, maybe it's up here buckling, but so what it buckled. It no longer takes, well, no, not so what. So it no longer take the load. That was part of one of my videos. No longer take the full load, transfers down 10, and we're back to around the circle. We're still down to this coming down here and here. But the buckling would have to take place behind that crane of all things. I kind of like the convenience of this bridge just failing under tension now. Just can't take it on the dead load. It can't take it. It resolves it down here because all the forces on number 10, indicating, going back to the screen, indicating that they were, here we go. What you got here? Careful with the blade. It seems the top of 11 moved, not the bottom. Yeah, well, they both moved eventually. So 11 failed first. I don't think so, Eric. You know, I like this. That was one of my videos that I can show 11. So there's multiple ways I can make. There's only there's a few ways I can make this. I can give you a lot of contributing factors that made it fail. I can 100% tell you that it failed here and here together. But then we want to throw in, well, was 11 the cause of it failing here, or was it just the dead load of this that overpowered the longitudinal post-tension cables and resolved itself here, based on the data that this was obviously had a lot of tension in it to support a lot of load from from the lower deck. Again, I'm repeating myself because people were walking in on it. So that this had 4 post-tension rods in it at 389 kips. Disclosed, in the drawings. Who knows what they ultimately did. And so this is 4 times 4, and I'll do that in brackets for you. All right, so 4 times this. This only had 2 going on, and it was designed to be detensioned. So this is just going to be under compression. But this one was obviously had all these with the intention to hold these 2 together. And it did an awesome job as it collapsed. I mean, I think the simple data shows itself that it's from here to here. We can add 11 here, but you can't do anything here for me. You can't give me any sliding action. Now, if you could tell me 12 kicked out, that could be a starting action. So 12 would start kicking out. If this goes together, if it moved just a little bit, look what it does to 10. It puts forces down there. It puts forces. It transfers the load, puts us under compression, right? Because it has an arching thing. But you would think it would fail more so here. But we can play along with that. If we can get 12 to lean that way, and we can do that if we start theorizing that they finished number 2 on the far end. They finished the post tensioning on number 2, and they say this thing could have a racking action. But number 2 was pulling in that direction at that point. Well, theoretically, it was pulling in that direction, right? It's going down, but also. We're talking about a design at this point. We know it 100% failed, and we're talking about, well, how did it fail? Well, now we're talking about the video trying to blow us off on that they want to. What's their agenda? What's their agenda to point there and not to be so precise? It's here. They want to be the first that reported it that way, or as someone wrote me, are they being bought off by the lobbying to now go with that because then they might have a setup to say, oh, we can call this the visible bird somehow. Lord, I love the Hallelujah song. Your page. Okay, move on. Back to this one. Okay. P, you still hiding out there, man? You still there? P 2015. All right. So oops. All right. Chime in. So thank you. The tension work would have pushed it over the edge. All right, so the quote is from Linwell Howell in Austin. He's the engineer there in Austin who's coming forward now. Contract to inspect bridges for the state of Texas. So this guy's the bridge inspector. They contract engineers to do inspections. The deck was post tension first. I'm over here reading, causing compression. Then 10 is post tension causing compression. Would post tensioning 10 after post tensioning the deck alter the load on the deck? Yeah, I talked about this, that chaos mathematics stuff. So let's jump onto him. That one there. So you got a cable going here. Ooh, here we go. So you've got this cable. Let me make sure you guys can see it. Let's call that the longitudinal cable, right? So it's got 1, 2, 3, 4, 5, 6, whatever it is, all of them there. And we got these guys. Well, what happens when you start pulling on this? Look at my right finger. Look how I'm going past that. If I start pulling on it, I'm creating a node here. I'm creating a load point, the chaos mathematics. I'm pulling across that one. It's no longer just working on this. I'm actually giving it a new point of pulling away from it. And also I'm giving it a load point coming down based on what these loads are that would be coming down here. Now, we say it's under tension. It's not like you can go up through it and lift it up with your hand because it's under tension. This thing's got dead load on it. It's still got a load coming down. It's still got forces coming down. And I don't claim to know if mine is under compression or not, but I would think it would be. Because that would just make it just too much tension and tension, what's going on there. So let's just say that's under compression. You're creating a load there. You're trying to make it out to there. Is number 9 a contributing factor? Load coming here, and then we go out to here. Tension between these two resolved right here again. We know 100% something's being resolved here and here. We're just trying to figure out how it got there. We know 10 did not compress. We know 11 and 12 did deform. How did 11 and 10 deform? Well, back here is where everyone's clowning around about it. And I'm willing to fight anybody on any engineer. And you can write me on the side, and I'll detract all my videos if you can show me, every last one of them, if you can show me how that sheared across PVC pipe without damaging it. Across PVC pipe. I can show you it hinged and lift off of it. I can show you how it hinged and lift off. It just came down, just rotated, and pulling downwards. We've already got a lift off right here. Already lifting off of everything, kicking this out. These photographs, I'm going to go back to the thing again. You'll see that there's curvature here in the rebar. I can find that real quickly for you guys, and because I think I have it ready to keyed up, if you will. Let me do that. Okay. I have an idea where the screen is. And what we have here, if the deck was posted right, so we talked about that. Joseph, I think there will lobby to have the same appearance bridges to replace this to save. Yeah, we talked about that yesterday. I forget who said that, or 2 days ago. And so right here, stress deck longitudinal tendons D1. That's the series of it, how they were doing it. And then C2, etc. They're going to go to bottom deck first, one post tension rod on each side of these guys, and then they were going to go to the top. What do we have here? Okay. Temporary supports of the main span section shall, not should, must, I'm not should or anything else, optional. It says shall. Temporary supports of the main span shall stay in the middle of the cross section during SPMT transportation. That's the whole thing right there. That's the whole thing in a nutshell. That's what they should be focusing on, that the plans were not followed. So then we ask ourselves, who's doing the lobbying? Well, I think MCM is doing the lobbying. If lobbying really exists, and as its reporters exist, I think MCM is doing the lobbying. And now here's the tie-in. If FIU is so not FIU, I keep saying the wrong. If Miami Herald's so awesome and great, why don't they track down who's doing the lobbying? This sort of, the conspiracy thing. When you go down that line, you go, wait a minute. If they're trying to get all the data, how come they're not trying to figure out who's trying to be the puppeteer? And that's the amazing part now, that there's no puppeteering links to this. So that puppeteer is badass, aren't they? And so there we go. Moving on to the next one. And here's the image right there. That's the coming over to it. So there's our curvature of our, let's use the blade. Right here, where my blade is, the curvature of the top. That's when the deck slid down. Right there is the PVC pipes. There's the deck. Number 11 was supposed to, oh, that's pretty cool. Look, this will be the number 11. We're supposed to come by and cut these off. It's sheared. You can look up PVC and try to figure out the forces it takes to shear PVC, and you will see that it obviously never could have done that. We do see a break here in a piece of PVC behind this one, so you didn't get to that one by going through there, right? So we have the bars here standing directly straight up. Now I will say again that anybody can show me that shear through there. You get to make me remove all my videos on this topic. That's how strongly I stand by this. So PVC, it's about 700 pounds or so of shear force to go through it, to go through that. Obviously, it came away from that first on doing the collapse. It pulled away as it collapsed downward and then rested on top of the pier. This went down to the ground. But note where this top piece of rebar right here above the, let's see if I can do it this way. Right here, this rebar right here, that shows you the angle that how far over number 11 and 12 bent down. Correction, that would be number 12, because that's in number 12. How far number 12 bent over at one point. I say at one point because it slid down the wall and therefore it deformed. Let's see. It slid down the wall, so it probably was like that at one point, and then as it slid down the wall, it came straight like that, the back side of this. But this obviously did not slide down the wall, the top, this curvature here. So that's some awesome data there, and we can get the size of that, and you can calculate how much it takes to bend just that one piece of rebar alone. And then we have the others in the same curvature format. See them? They're all doing the same deal. And you can calculate the forces it took to rotate that. You can calculate the forces it took to rotate that. Now, I said number 12. We can move number 12 out of the way, right? And let's just make number 12 be the culprit. Move 12 out of the way. Well, you can move it out of the way you want. If you do that, you're shearing all this backside of that rebar. It's coming up here, right? Out of the bottom deck. Well, just by moving that over, you're shearing this off. So you're getting the tearing of the concrete in here. But you're also no longer able to get the curvature of the rebar because you went that way first by doing that with 12. So clearly, that now I'm not going to say clearly. You guys can interject going, wait a minute, you're missing something. You know, I'm open for some banter here, some data. All right, let's go on to the next one. This one's kind of cool. And we're going to keep this one, Danielle. We're going to keep this one just about this video, so because I couldn't upload the other video properly. You know, the fireman kept looking down the hole. Look at this hole now. We actually have access to the hole. There's one image I found. You see the reinforcement, and you see that it's you see the through behind on the bottom. This is the south side of the node, if you will. Where's my blade? Yeah. So we're looking through the node now. Right there. That's what they were looking through. I guess they were just curious because we know no one was down there. Well, they didn't know it at the time, so. But what don't you see? You know, you take data on it. I mean, I would love to see the photographs in that. Oh, there's my cap too. See the infamous cap, the hard hat. Damn hard hat. Hold on, I'm refocusing. There's the infamous hard hat. and I'll look at your comments in a second. If you guys want me to zoom in on anything like that, you've got to speak up, and I'll go back to it. This is the questions and answers and a banter and fun against each other, having a little conversation. And let's go. So there's the, right here, there's the 2 pieces of reinforcement, 1 and 2. I'm making sure you guys can see that because I have to go to my laptop and then back up to the cell phone to talk to you. Yeah, look at that. So, did that fail? Is that what they jackhammered into, the grid access? And look at the location of it. What a heck of a design. And, and there we go. Now we see the cool. They didn't care about the loads at that point. Here's the entanglement, if you will. So when I do the rotation and the final ending of everything, data you guys can snatch up. We see that the post-tension rod is sitting up there. Let's focus it. I'm gonna go around there. Good, that's focused. We see the post-tension rod sitting here. That's the end of it. We see this crack here. We see all as the hinge happened, I believe, and then also coming down here is this action on top of this caused some debris. Now this debris fell down on top of that deck, I'm sure of that, and because of gravity, right? And probably the NTSB, when they're B-roll, for the B-roll, they removed some of that concrete, so we don't have access to see it before that, to see where it was going. But I did look at the back of the canal shots, and I couldn't find any image, because who's going to clean up back of the canal, right? So I didn't find any concrete in the back of the canal. I'm trying to zoom out. Give me a second. There we go. And what you got for me, P? I see your comment. Give me a second. Give me a second. Trying to focus. Okay. Danielle, can you with your paper model move top of 11 first? Yeah, I can do that. Yes. And what if the node failed? Yeah. Yep. That's what we're talking about initially in my videos, the node failing as part of the whole thing to make the whole thing start where it no longer passes load. The canopy C1. Okay, so let's do that. So once you see the top, so one of my videos I really said behind the crane that what happened first was, and this is what, who's saying this is C1, who, can you, where is it? Right, this is Scott. Yeah, Scott, so I theorized behind the crane, this crack happened first while they were post-tensioning it. And I did that in the last live video too. So, and I'll get there this way then. So then we know they post-tension the top one. I'm just reading the message. It is known that the post-tension rod in 11 broke. Is it known? No, there's no known. All right, so like that. And then we have post-tensioning here. As we talked about, give me a second, drawing off screen here. And coming back on screen. Yeah, Tim, I shared that post hoc and all that. There's a saying, just because one thing happened doesn't correlate to what you think happened. So I got to use that in my mind. I can't say just because I saw that action, that caused the whole collapse. We would love to say that initially, but if you try to find it, you have to, if I'm being the way I am, I have to see, okay, what if they are definitely a responsible party, a contributing factor because they're VSL. VSL is a professional bridge repair company also. You know, that's what they're designed to do. So with that said, they can't claim ignorance by orders of Denny Pate because you can't make me take a jackhammer to this bridge, right? If you said, hey, go up there and start jackhammering this, obviously I know that's going to cause some structural problems, so I shouldn't do it. I think Denny Pate was telling them to close cracks up. At that point, they should have kicked in their professional hat saying, hey, this is our wheelhouse. Let us evaluate this longer before we start filing orders from you. But as I understand it, they got 300 and some change, 300, they call it 350K. And so, you know, you're going to follow orders, you know, if you want another job. So let's go with number 11, as someone just said, failure, right? So I'm looking through the camera as I draw. So this is the post-tension bar we know completed. This creates compression force. If I was to do a beam, right, like this, and we put a load on it, tension with this, if I put compression up here, I'm creating a force down here that's a tension action. Look at my hand. So if I'm creating it like that, if you will. So I'm trying to, come up with the crack force up here. So to do that, and I said that in another video, you tension this one, and some reason this node, looking up here now, the node, when it was tensioned, it decided that the force is needed, and maybe we had existing cracks. I got to do some leap of face here. And there was a crack here, and when you did that, it opened it up. And I think I showed that by helping people understand it by grabbing a pen and putting them end to end. And imagine me pushing on these pens, which I'm doing now. So that's the post-tensioning. But all it would take is me post-tensioning the top of this. And now you see the bottom open up? Let's do that. Let's come closer and closer and closer and turn. Oh, this is a lot tougher than it looks. Okay. So as I post-tension the top, I'm opening the bottom. I'm exaggerating it, of course, but the forces, if I'm only on on the top half of this, the forces are in that direction, are acting like that manner. And if you remember, in one of my videos, I talked about how the post-tension rods in this one are so well, I can't call them imbalanced, right? They're designed, but they're just at the top and bottom, and I would say that's the worst place you could put them without tension them balancing back and forth, because by putting it near the top, you just created that action I just showed you with a pen. So this is number 11, in our theoretical conversation here. So it's at the top. That's creating that forces there. If it was a crack there, we would get no longer load. So I'm talking to Scott, I think, and everybody obviously, but Scott's question. So no longer we're getting the loads transferring down here evenly. They've now been kind of redirected because of this post-tensioning here. It's actually making an opening there with the crack alone because of the forces in there. It's still compressing. It's not pushing anything away, except for to do it. It's gonna create a little bit of action going on. That little bit of action because I just said it's doing this, right? And everything's connected. So if that's connected, and I create just a little bit of forces like that, where the force is going? Down 10. Goes to the node, pushes down 10. We're going around a circle again. We're back to here again, where then the forces are resolving themselves. So yes, the post-tensioning of this one could have contributed. And then, because not being balanced, a crack would have to be sort of present. Otherwise, I'm going to have to, with this, I would say the failure would be near the middle at that point, all things being equal in this post-tensioning system. Then the bow would have that same action I show up here would be down here. We've got an existing member, going back to the TV screen, the movie screen, or whatever the heck this is. Going back to this, we've got no brakes in there to speak of. What I'm reading, Lord? Jeff. So am I supposed to read that when it's comment to somebody else? I'm just a plumber trying. Well, we said that, Tim. Okay. What would have happened if 10, 11 punched through the canopy at the start, cascading failures? It didn't punch through the canopy. Well, no, I don't think it punched through the canopy. The node didn't completely separate from the canopy, but it lifted. That's Jeff. We'll get back to you, Jeff. All right, so this is awesome. We don't see any breaks here or here on the back side. I looked at a lot of images. This looks like a straight piece of material. It doesn't look like there's any brakes in it. So yes, we'd have to put that brake up here still behind this truck, right? That's that way to nature the beast. And also down there. Well, dealing with down there, we dealt with it. Now we're dealing with up here. That's the only wild card because we couldn't see behind it. The images, the crane. So surely, and surely, I'm making fun of that movie, the airplane movie, where he says Shirley. My name's not Shirley. What's his name? Kareem Abdul-Jabbar. Yeah. Anyway, so surely, that's an option that we have to leave open. Sorry, back to this. That's an option we have to leave open that could have contributed. But again, going with the knowns, 10, as the bridge is breaking, is clear. There's no deformation here. This is clearly a break and a clearly break. If you time the video and slow it down a million times, which I've done, I can't see a break between each one of them separately. I can't see an individual break, which means this number 10 clearly worked. That means the node clearly worked, keeping it together. Remember, the data shows that this cracking more than likely didn't take place here. Forces were in a plate form, where I have cracking up here many times. That if it was in there, I'd like to see a break over here. Something going on the side. So we got to go to where it cracks, right on the side of the node. And right about here somewhere, I don't know, here. I can't quite make out where this break is fully. Question, Leslie Nielsen, that's it. Don't call me Shirley. Yeah, thanks, Tim. Yeah. Have you ever seen that grown man naked, he said? Didn't he say that in there too? They can never say those in movies these days. All right, so let me look at the images. So we look at I'm gonna load this next image up for you guys right here. I'm going back to let's look at this. First off, I'm using a scaled model that doesn't have this, that doesn't have the sharp angle, this little bit of addition they put in, or a piece of concrete they put right across here. This is the model from 2016. It's the only one I could find that would get me close enough. And Tim writes, Peter Graves, have you ever seen a grown man naked? Oh, Tim, you are awesome. When two competing teams present their plans for the bridge, in 2015, only one struck Tom Gustafars, whatever his name is, at FIU's administrator and former Speaker of the Florida House, as matching the grandeur sought by the university. Okay, listen to that. The truth is out on that one. And the other thing is,